Okay, so we've discussed the basic properties of a PN junction diode, right? And what we saw is that in the forward bias region, you have an exponential behavior because what you do when you forward bias a PN junction, you're lowering the potential barrier, and due to the thermal energy, more electrons and holes from both sides can go across, and you can create more current. And that explains the behavior, the exponential behavior of the diode. Now, and in the reverse bias, we saw that we are increasing the height. We increased the height of potential barrier, so fewer could go. And what the current is dominated by, is essentially the thermal generation of electron holes mostly in the depletion region. That, due to the electric field, will be sent in the opposite direction, and that would establish the current. Now, one of the things that to keep in mind is now in this reverse bias mode of operation, we want to kind of think about the behavior of the thing. So we are going to talk about the junction capacitance and calculate that. So we'll talk about junction capacitance. Now, what do we mean by that? So let's think about what it looks like when you have some potential applied to reverse bias applied, or no potential at all, but just let's say it's reverse bias for the sake of argument. So you have the p-type and n-type, and you have the depletion region, within which you have negatively charged ions here and positively charged ions there. So, and this basically obviously establishes an electric field. Now, outside this region, you have mostly free charge carriers. So you have electrons in this region, and you have holes in this region. Of course, you have the ions sitting there. So from a net charge perspective, these regions are neutral. Yes?
Should the ions be like in the other way, like positive ions on the p-type side?
So the question is that or shouldn't the ions be positive on this side and negative on that side? No, but think about it. The n-type has more column 5 elements, right? So they have one extra proton in the nucleus. So when that extra electron, the 5th electron, is released, what's left behind is positively charged. Did I make a mistake? Yeah.
Maybe you hope to distinguish what you're drawing in the bulk is the free carriers rather than ions. Your negatives on the right here. The blue is the free carriers.
These are the free carriers, correct, yes. These are the electrons. So these are that is correct. So these are the free carriers, these are the electrons here, and these are these are the free electrons, these are the holes, right? And then this is what's left behind. This region is depleted. So what else you have here is that you have this negatively charged ions here and positively charged ions throughout this thing. I just don't want to draw every single one of them again, right? So but this in the depletion region, that's correct. And that's actually, if you look at it, it's consistent with the picture you had there, right? Okay, so we have this thing, and you can have some reverse bias applied to this. So basically, what you have here is that you have positive, so you can say this is some sort of a reverse bias. You can show it as negative VD. So let's do this. So this is a negative potential applied here. So this is negative VD applied here. So what does this look like to you? Remember, these charges are not mobile. They're not able to move, right? But these charges are. So now if I change this voltage a little bit, let's say I increase this reverse bias, what do you expect to happen? So there would be, this depletion region will grow a little bit. So the depletion region becomes a little bit larger. And as a result, you can basically have a larger depletion region. Or if I make this a little bit smaller, the depletion region will become smaller, right? But regardless, these charges can move back and forth. These are free charges. So does this not look like a plate of a capacitor? So this is like one side of the plate, and this is the other side of the plate, a parallel plate capacitor. Because you have free charges moving around. Yes, there are some built-in charges in the middle, but they're not moving. They're not mobile. So they're not going to be doing anything unusual. So if I ask you what is the capacitance of this, what would you tell me? You would basically say that this capacitance is essentially if it's like a parallel plate capacitance of this plate spacing. And more accurately, or alternatively, perhaps, if I say what is the capacitance per unit area, it is going to be determined by the spacing. So let's call that spacing xn plus xp, or xp plus xn. And epsilon s is the semiconductor dielectric constant. So the capacitance, total capacitance would be epsilon times area divided by the spacing. Now if I do it per unit area, it would be epsilon divided by the spacing of this capacitance. So if I want to find this capacitance, I need to find what the xp, which is this length, and what the xn, which is that length, are. Right? So those are the two things that I need to calculate for this calculation. So how do we go about that? So now we are making an assumption so far. The assumption we are making right now is that the doping concentration is uniform across this entire region, and it abruptly transitions to the doping concentration here. So on this side you have the Na, and on this side you have Nd, and that's constant. This is basically called an abrupt junction. A junction where the doping concentration is constant to a level up to a point, it instantaneously changes to a different level. Now, making such a thing is hard. You can make good approximations of it, but it's not, I mean, you cannot never make something exactly like that. Yes, question?
Doesn't that assume that all the charges are sitting on the plates of the capacitor?
That's a good question. It assumes that there's sufficient amount of charge that can move. But remember, this is not net charge, right? Think of this. This is a kind of a very good. This is a good question because it points to subtleties of this device. The net charge really is in here, but that's not moving. So this is what we call a small signal capacitance. It's an incremental capacitance. It's capacitance as far as the changes of the small changes in the voltage are concerned. So if I produce a change in the voltage, the charge that goes in or comes out is coming out of this region, which is basically it's produced by extension or shrinkage of the depletion region. So that delta in the charge is what's going in and outside of these terminals. So from a black box perspective, it will look like a capacitor because the charge in this part, in this edge, that's being pushed out or brought in. But still, since it's the charge at this distance, that would correspond to a capacitance with the spacing of plates. Okay? Does it make sense? Good? All right. So let's see. Well, let's try to calculate this. Let's try to see if we can actually calculate this capacitance. Yes. Question.
Basically, what you're saying there is, yes, it's actually the depletion region growing or shrinking, but you're doing like such a small incremental change in it that's effectively as though the separation isn't changing with the amount of charge.
Well, so the question that was raised is that am I saying that the separation is not changing? As we'll see, actually, is that we are assuming that change in the separation will come out in our equations. So I'm not making that assumption that this width is not changing fundamentally. What I'm saying is that the variations in the total charge that goes in and outside this device comes at the edge, from the edge point, from that transition point. So that's basically what I'm trying to say. So once we do the calculation, I think it becomes a little bit more clear what I mean. Okay, very good. So let's do the calculation. So what do we know? Let's look at the charge density, rho. So if you look at the rho of x, how does it look like versus x? So this is x, and this is the origin, right? How does the charge density look like? The net charge density, the total charge density. So I have positive charge here in this part of the depletion region, and I have negative charge here, right? Because I have the ions. Here I'm neutral, because yes, I have a lot of electrons, but I also have a equivalent number of positive ions, and likewise here. So what does that charge density look like? So you have, on this side, we have positive charge, say xn. Is this visible enough, or is it too faint for somebody? Good? Okay, xn, I try to push hard. And what is this height? What is this charge density? Which is basically coulombs per cubic meter. What's the value here? What's the height? What is the density of this charge? what is the density of these dopants here? ND, right? So the charge is going to be QND, the charge density, right? Coulombs per cubic centimeters or cubic meters. Now, the same way, also you can think about this side. And they don't have to be the same length. So this is negative XP, and this is going to be negative QNA. So this is negatively charged, and this is positively charged. So that's the charge distribution. That's the way it looks like. Okay? So if this is your charge distribution, let's talk about what we are trying to do before we jump into equations. What we are trying to do is to find this potential, electric potential, as a function of xn plus xp. And then use that to solve for xn plus xp as a function of the electric potential, and then plug that xn plus xp that we calculated back into this equation to find an expression for C in terms of the electric potential that's applied. That's what we're trying to find. We're trying to find an expression for C as a function of Vd. That's what we are trying to do. We'll write a bunch of equations now, but that's where we are going with them. Okay? So now that we know where we are going, let's go there. Okay, so we know the charge density. If I want to calculate the potential, electric potential, what's the next thing that I have to calculate versus function of, as a function of x? So from charge density, you can calculate electric field. And from electric field, you can calculate the electric potential. You integrate every time you want to do that, essentially. It's integration twice, right? So if this is your charge density, what do you think that electric field will look like? So your electric field obviously is pointing in this direction, so it's going to be negative, right? And so I have uniform charge density. Let's say, what is the electric field here? In this plane, where my hand is. This cross-section plane, perpendicular to the whiteboard. 0, right? Because there's no net charge around. 0, 0, so as I move up, it's 0, 0, 0, 0, 0 here. As soon as I get here, what happens? Now I'm getting some negative charge on this side and some net positive charge on the other side, because there's now less negative charge and more positive charge on that side. So there would be an electric field growing in that direction. So, and it would grow linearly, right? So I would expect it to do something like this. Let's use a different color. So it will grow linearly, and obviously it's maximum here at the junction, because I have all of the negative charges on one side, all of the positive charges on the other side, and then it will grow back to 0 at xn, and this is negative xp. Now the question is, what is this maximum, this Emax? What is this maximum electric field? Well, you can do it from Gauss's law, right? From Gauss's law, if you form a Gaussian surface, one on this side and then one on the other side, and electric field is going this direction only. So what you have is that you have 0 here. So this is basically the electric field here. It would be sigma, the total charge density, divided by epsilon, right? So what is sigma? What is the surface charge density? It is basically the volume charge density times xp, right? So Emax is going to be q xn nd divided by epsilon of the semiconductor, which is equal to q xp Na divided by epsilon. Now you also know something else. Obviously, the total net charge on this side and that side have to be equal. In other words, the area of this rectangle and that rectangle have to be equal, because you started with total charge neutrality, right? Now, what happens is that, so basically what that means is that xn nd equals xp Na from that. So now what I'm trying to do is express Emax in terms of not just xn or xp the way it's written. So I'm going to try to express it as in terms of that, to make it more symmetrical. So this is what we are going to be doing mathematically. So basically we are going to write the xn plus xp in terms of one of them. So how can I do that? Well, I can write it as xn plus, now I can solve for xp from this and plug it back in there. So I can write it as xn times nd over na, right? Which I can write as x, then it would be xn times na plus nd divided by na. So that's my, so that's xn in terms of that. So xn is, so now I can solve for xn between these. I can say xn is na divided by na plus nd times xn plus xp, right? I'm just solving for xn in terms of that. And then now, what I really need is xn times nd. So I can multiply by nd. So I can multiply both sides by nd. And I will get this. Now I take this and plug it into this guy. Okay? So what we will get then, as a result, is that now E max, the maximum electric field, is going to be Q over epsilon of the semiconductor, Na Nd over Na plus Nd times Xn plus Xp. So I have expressed my Emax in terms of Xn plus Xp. And you can see now it has become symmetrical in terms of the N side and P side, right? So it captures both sides of the expression. So that's half of the thing. Now the other half is basically now going from this to the potential, electric potential. So now we've calculated, so this was E. This was a plot of the electric field. This was rho, the charge density, E of x. So now what we are trying to do is to calculate the electric voltage or electric potential, right? Psi of x. So how do I, if I know the electric field, how do I calculate the electric potential? Again, it's an integral by definition. So it basically, if you integrate this, you basically integrate a linear, then you get quadratic, right? So you get a quadratic here and you get a quadratic there. So this is going to be psi, it would be psi n, and this would be psi p. Now what are psi n and psi p? Well, they are simply the areas of these triangles. The area of this thing is psi p, and the area of this thing is psi n, because that's the integral, right? So what are those areas? Well, what is the area of this thing? So psi p is going to be xp E max divided by 2, and psi n is going to be whatever, xn E max over 2. Is it clear? Right? Good. So we are almost done with that. And all right, so now so that's the, so but, and the total difference of psi n and psi p is the total potential across this thing. So now in general, if you have a negative bias, this whole thing would be psi 0 minus Vd, right? Now, so that's psi 0 minus, that's really faint. Psi 0 minus Vd. All right. So we're almost done. So we know what psi is. So we know that psi 0 minus Vd is equal to psi n plus psi p, which is now equal, we know is equal to E max over 2 times xn plus xp. But we already know what E max is in terms of the parameters of the design. We will plug that in, so we'll get Q over 2 epsilon silicon, Na Nd over Na plus Nd times xn plus xp squared. And now what we are trying to solve for is xn plus xp to plug back into this guy and get our capacitance as a function of Vd. Because now we have, these are physical constants, these are design parameters. We'll solve for xn plus xp, and this is the voltage and the built-in potential. And then we plug it back into this guy to solve. So all we do is just basically say that xn plus xp is going to be that thing, psi naught minus Vd, divided by q to epsilon naught. Let's just make it simple a little bit. 2 epsilon naught over q, 1 over Na plus 1 over Nd, psi naught minus Vd to the power of 1/2 square root. And then we plug it into that thing, and then you get your capacitance. So our capacitance is epsilon silicon divided by that. So when you do that, so not epsilon 0, sorry, epsilon silicon. Or epsilon semiconductor, more accurately, not silicon necessarily. So what you get when you divide it by that is basically you get a full expression for it. You will get q epsilon silicon divided by 2 times 1 over Na plus 1 over Nd psi naught minus Vd to the power of 1/2. Yep. So you get this expression, which you can also write as this. You can write it as Cj0 divided by 1 minus Vd minus psi naught to the power of 1/2. And Cj0 is essentially Cj when Vd is 0. So you can write it, express it in terms of its value when there's no, the external voltage is 0. Cj0 is Cj for Vd equals 0. So we are done with our equation writing phase. Let's see what it means, because equations are useless unless you know what they mean. Right? I mean, just so what do these equations mean? What do they imply? What are they teaching us? So we are learning a few things about the junction capacitance. Right. First of all, the depletion width, the width of the depletion region, is related to the silicon dielectric constant. Fine, sure, but, or semiconductor dielectric constant in general. So that you can't do much about. It is what it is. It also depends on the doping levels, right? So if you wanted, for example, let me ask you a question. If you wanted to make the depletion region narrower for a given voltage, what should you do to the doping concentrations? If you wanted to get a narrower depletion width, increase the doping, right? Now, if I increase the doping of one side, what happens? If, let's say, I only increase Na and not increase Nd, what would happen? You will shrink just one side of it, right? Now, so let's say if I had increased Na, this rectangle would become like that. But still has to be equal to the other side, which basically means that, now this is an important statement, so pay attention to it, that the width of the depletion region is dominated by the lightly doped side, or by the lighter doped side. The side that has a smaller doping concentration will dominate the width of your depletion region. Now, if you want to shrink it, you have to scale both of them down. And this is important when we talk about scaling of devices, when you try to make them smaller. If you want to make the device smaller and you want to keep the relative sizes of the depletion regions more or less the same, what it means is that you need to scale both concentrations by the same amount up. And you push it up, 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 up. Now what happens, so that's fine. So we make the depletion region smaller. But if you make the width of the depletion region smaller, what happens to your capacitance? You can see it more easily here, but you can also see it from NA and ND. What would happen to your capacitance per unit area? It goes up. Now, is it a good thing if you have a lot more capacitance per, in your device? Or a bad thing? It depends on what you're trying to do. But if you're trying to make an amplifier that operates at higher frequencies, we'll see that that capacitance is not a good thing. So what do you need to do? So is scaling doomed because of that? No. Why? Why? Why isn't scaling doomed? Or at least for a long time it wasn't doomed till you hit atoms. Just, yes?
You can scale the area as well.
Correct. You can scale the area as well because this is capacitance per unit area. So yes, the capacitance per unit area will go up, but if your area goes down, at least proportionately, then the total capacitance will not go up. Of course, you want the total capacitance to go down if you can, because then that makes the device faster. And we'll see a lot more of these trade-offs as we go forward and how they interact with each other. But this is important. So the depletion region is dominated by the lightly doped side. And the total width is dominated, of course, by the side. If you want to make it narrower, shrink it, you need to make the concentration smaller. Now, this exponent, I have another question for you to think about. What dictates the value of this exponent? What determines that value? Where did that square root came from? Where did it come from? Yes?
Well, we had to integrate the area of those rectangles, which gave us...
Sure. So we started with straight lines, essentially constants. We integrated once, we got linear. And we integrated one more time, we got quadratic. So there was one assumption that led to this square, which led to the square root, which gave us this square root, which is the same square root. Right? Yes? We started with a uniform or abrupt junction, right, as we both pointed out. So now, let's say if I were to start with linear doping concentration as opposed to constant. So let's say my doping concentration looked like this. So it's called linearly graded junction. Now, what would you say that this exponent would be? 1/3. 1/3, right? Because you're starting with linear, you will get quadratic here, so this becomes quadratic, and then this becomes cubic, and therefore that becomes one cubic root. So this exponent is really, it tells you something about the profile of the junction. In fact, from that measurement, you can actually determine. The measurement of this capacitance is the prominent way of determining or measuring the profile of a junction you've made. You measure it for different values of VD, which basically shows the profile at different distances, because that's the variations here versus variations here versus variations here for different VDs, because they produce different junction width. So if you wanted to measure where the value or the profile of the junction capacitance, this would be the way to do it. Now, this is an important parameter. Now, this capacitance, if you look at this capacitance, this is not a linear capacitor, right? This capacitance depends on the voltage across itself. So it's a nonlinear capacitor. Now, it may be a good thing or a bad thing, depending on what you're trying to do. So if you're trying to make something that's very linear, and you introduce a fundamental component into it, you may see harmonics in your electronic devices that may be coming due to this nonlinearity of this capacitance. There are also a whole bunch of other nonlinearities in the devices, right? I mean, for example, you have an exponential current, voltage behavior, and things of that sort. But this can contribute to the nonlinearity if you take care of some of the other things. Now, it can be a good thing if you're looking for a nonlinear capacitor to do something. For example, if you're looking to change the capacitance, you are looking for a voltage-controlled capacitance, right? It's called a varactor. So in one of your homework problems, you will deal with that. And not only that, you will also design a profile that would give the circuits that designed with that varactor a certain preferential behavior. So this, when you do that, you realize that, okay, well, these are not the only two profiles you can have. you can make a certain profile that would give you a certain exponent here that may or may not do something useful for you at that point. So that's part of the engineering part of it. You have to understand the analysis to be able to design for that. All right, very good. Any questions?
Physically, how do you make a profile?
Okay, very good question. So the question is, how do you practically make this? We will talk about this when we talk about fabrication in more details. But in short, there are different ways to do this. One is, when you introduce these dopants, how do you do that? In the old days, what they did, they grew a glass that was had a high content of the dopant you wanted to do. For example, if you had like boron or arsenic or something like that, you infuse it. And then you heat it up to temperatures, very high temperatures, like 1100 C or something like that, below the melting temperature of silicon, but close. So these carriers now start, due to their thermal energy, move in there. Or in other words, diffuse, or diffusion. Due to diffusion, they would just diffuse and go inside. And by controlling the temperature and the time you had that going on, they would perform a certain profile. And then you introduce a second layer, which was the opposite, and they would go in and settle at a lower depth, and they would form a junction. So that was the old days. Now, today, most of the times, what you do it with ion implantation, which basically means that you ionize the carriers that you want. You put them through an accelerator, particle accelerator. Basically, you just have two charge plates or combination of them. You accelerate them to a certain energy, measures in kilo electron volts or something like that, and just smash them into the silicon. Now, by controlling that energy and density and the angle at which they come in, you can actually create different profiles at different depths. And then after you do that, you anneal it. Basically, you raise the temperature so these things start jiggling around and then going and falling into the right place. So the crystal damages that you've done are repaired. And then they will stay there. So you can actually create a profile by smashing some deeper ones and at a higher energy and the lower energy ones. So that's why you can never actually make this exact thing. You can make things that are close to it, but you can also create any profile you want, or some approximations of any profile that you want, by controlling these levels of implantations, how many you have. At some point, it may become impractical. Say, well, I want this, yes, you can do it with 20 different implantations. If you have the money to pay for it and the time to wait, yes, sure. So there's a trade-off between practicality of the number of these things that you want to do and the accuracy that you want to achieve, right? But those are the ways. And there are various ways of doing this, and the fabrication process is a field of its own. I mean, just how you fabricate these things. And there are lots of different steps involved in it. We'll talk about some of them briefly. All right. Any other questions? Okay, great.